Written in the 2nd century CE, Claudius Ptolemy's Mathematicae Syntaxis, better known as the Almagest, became the most important text in mathematical astronomy for the next 1500 years. But despite the historical significance of this text, it's nearly impossible to find detailed information on how its models were derived and functioned. So much so that when I began studying historical astronomy, I decided it was best to sit down and work through it myself. So in this series, I'll share what I've learned about one of the most important astronomical texts of all time. I'll begin by addressing things conceptually, so viewers that aren't interested in the detailed mathematical workings can get an appreciation for Ptolemy's work. With that out of the way, I'll then explore select mathematical topics, taking the understanding from conceptual to functional, allowing viewers to understand how the models were practically applied. In this video, I'll be exploring books 1 and 2 of the 13 books that compose the Almagest. In these, Ptolemy lays out his philosophical assumptions, develops several handy tables that he will rely on to make calculations easier, discusses his place on the terrestrial sphere, and explains how location influences our view of the cosmos. So join me as we learn how Ptolemy defined astronomy before the telescope. Ptolemy opens the Almagest addressing Cyrus, to whom a number of Ptolemy's works are addressed. However, historians have no idea who this individual was and if he existed at all, as the name is rather generic. Ptolemy then launches into a brief discussion on philosophy. It begins with moral philosophy, which, Ptolemy tells us, individuals can possess some of the moral virtues, even without having been taught. He contrasts this with natural philosophy, in which it is impossible to achieve a theoretical understanding of the universe without instruction. He then discusses how Aristotle breaks theoretical philosophy into 3 subcategories: physics, mathematics, and theology. Ptolemy sees astronomy as touching on all 3 of these. Specifically, the cosmos has various motions associated with it. One may ask what the first motion was, which Ptolemy immediately states can be viewed as caused by an invisible and motionless deity. Thus, astronomy is theology, which is completely separated from perceptible reality. Second, we could ask about the nature of the various things in the classical Greek sense. Ptolemy labels this as physics. Lastly, the investigation of number, size, place, time, and such like he describes as mathematics, which he takes as the only true knowledge, since the other 2 are not directly observed, but rather approached through logic and intuition. Only mathematics provides proof through indisputable methods, namely arithmetic and geometry. Mathematics, he says, provides a means for investigation of theology and physics, allowing men to see clearly from the constancy, order, symmetry, and calm which are associated with the divine. Next, Ptolemy lays out an overarching vision for the text. He tells us that we'll begin by discussing the position of the ecliptic. Although he doesn't explain it here, this is the fundamental plane for Ptolemy, as the Almagest is largely interested in the motions of the sun, moon, and planets, which all remain close to the ecliptic. In short, the Almagest will use the ecliptic coordinate system instead of the equatorial coordinate system. Next, he says he will discuss the regions of our part of the inhabited world and the features differentiating each from the others due to the varying latitudes at each horizon. In short, Ptolemy will first present many fundamental relationships along the equator where things are simple, and then discuss how changing your latitude complicates the view of the sky and the various circles within it. Then, Ptolemy will discuss the sun and moon, followed by the phenomena accompanying these motions, by which he means eclipses. From there, Ptolemy will discuss the fixed stars before discussing the 5 planets. But before doing that, he tells us that we'll need to make some underlying assumptions and observations about the nature of the cosmos. The first is that the heavens appear to move like a sphere around us. This is essentially introducing the concept of the celestial sphere. Ptolemy justifies this by noting that the stars all seem to rotate around a pole exactly in the manner we should expect if we were at the center of a sphere, being rotated around an axis in which those stars which were closest to the pole revolved on a smaller circle, while those that were further away described circles ever greater in proportion to their distance. Of course, from any point on Earth, we can only see half of this sphere at a time. So how do we know it's not just a dome? This would really be best addressed by noting that the horizon is an illusion, and that the Earth is a sphere, so domes for every horizon amount to a sphere. But Ptolemy hasn't established a spherical Earth yet, so he doesn't take this approach. Rather, he states that if the sky were only a dome, this would mean that the eastern portion of it would have to generate the stars, while the west side extinguished them. Ptolemy calls this a completely absurd hypothesis, as it would necessitate the generating process recreate the stars in perfectly the same positions, night after night, and he assumes that any generative process would be too chaotic for this. Furthermore, there are some stars which never set, known as circumpolar stars, and those individuals who would claim that the stars are generated and extinguished fail to address these. He hints at the sphericity of the Earth, noting that the number of stars which are circumpolar differ for different observers at different latitudes. In the next chapter, Ptolemy does address the fact that the Earth is a sphere. As evidence for this, he states that the sun, moon, and other stars do not rise and set simultaneously for everyone on the Earth, but do so earlier for those more towards the east and later for those in the west. This is a rather interesting thing to tease out without reliable clocks that can be compared against local time as determined by the sun. But it is easily demonstrated by observing the timing of celestial events like eclipses from different longitudes, which is precisely what Ptolemy uses as proof. He notes that eclipses are not recorded as occurring at the same hour by all observers. Rather, the hour recorded by the more easterly observers is always later than that recorded by the more westerly, and that the differences in the hour are proportional to the distances between the places of observation. As further proof, Ptolemy also notes that when one sails towards mountains, they seem to rise out of the ocean, beginning with their peaks, due to the curvature of the Earth. Ptolemy next discusses the location of the Earth in the cosmos. Here, he adopts a geocentric position, that the Earth is the center of the cosmos, and presents arguments for this. The first is that if the Earth were displaced, it would cause the timing of the equinoxes and solstices to be different. Additionally, if the Earth were closer to one side of the celestial sphere than another, we wouldn't see precisely half of the celestial sphere at a time, as the side we were closer to would dominate our local sky. There's a few hidden assumptions here that are where Ptolemy goes wrong. In particular, Ptolemy's argument regarding the equinoxes and solstices assumes that the motion of the other objects is more or less centered in the cosmos. Furthermore, he, understandably, fails to appreciate the size of the cosmos. Our solar system is so small in comparison that even though the Earth does move, its motion was impossible to observe until the 19th century. In Chapter 6, Ptolemy argues that the size of the Earth is insignificant with respect to the size of the heavens. In other words, no matter where you are on Earth, you're effectively at the center of the cosmos. You don't have to worry about your position on the Earth bringing you closer or further to one side of the celestial sphere. This may sound rather unimportant, but it actually becomes relevant for some of the math later on. However, there's also a notable exception for this, as the Moon displays a notable parallax due to how close it is. Ptolemy then argues that the Earth does not move. Essentially, Ptolemy is stating that the Earth cannot orbit the Sun. And the reasoning he gives here is the same arguments as the preceding ones regarding the centrality of the Earth. However, he also provides a further argument based on the observation that anywhere on Earth, objects seem to fall down. He assumes that downness is an essential property of the cosmos, drawing everything towards its center, and that the Earth has settled with its center coincident with this cosmic center. He states that light and rarefied bodies drift outwards towards the circumference, but seem to move in the direction which is up for each observer, since the overhead direction for all of us, which is also called up, points towards the surrounding surface. Heavy and dense bodies, on the other hand, are carried towards the middle and the center, but seem to fall downwards because, again, the direction which is for all of us towards our feet, called down, also points towards the center of the Earth. A further consideration in this chapter is whether the Earth rotates, as had been suggested by Heraclides of Pontus in the late 4th century BCE. Ptolemy rejects this, noting that the clouds do not get left behind as the Earth rotates. Again, Ptolemy had no concept of inertia, and assumed that they would tend towards rest without a force sustaining their motion. With the previous assumptions in place, Ptolemy is essentially done with the starting assumptions. The rest of the book will be based on observations and mathematical reasoning. And the first observation that Ptolemy gives is that there appears to be two primary motions of the heavens. The first is what we might describe as the bulk motion of the night sky, in which things rotate about us from east to west every day. In modern astronomy, we recognize this as being caused by the rotation of the Earth. However, since Ptolemy assumes that the Earth does not rotate, he takes this motion to be produced by the rotation of the sphere of the stars about the Earth and refers to it as a forward motion. This rotation takes place about the poles, which naturally produces a great circle known as the celestial equator. Ptolemy informs us that it is called the equator because this celestial great circle is always bisected in two equal portions by our local horizon. The second motion is the motion of the sun, moon, and planets. While they generally get carried across the sky every day, if we pay careful attention, we can find that they tend to move west to east amongst the background stars. This is generally easy to observe for the planets and the moon if you watch for a few nights. Unfortunately, the sun blocks us from seeing the motion against the stars for it, but we can observe that the same stars rise about 4 minutes earlier each day, which is another way of stating that the sun rises 4 minutes later each day due to its west to east motion. In truth, a 360-degree revolution is actually occurring in about 23 hours and 56 minutes, but since we reckon time by the sun, we add those 4 minutes to bring a day to 24 hours. Ptolemy considers whether this second motion is truly independent and concludes that it is, given that it's not simply that these objects tend to move a bit more slowly. Rather, their motion is along an entirely separate path, the ecliptic, which is also a great circle with its own poles. The intersection of these two great circles, the celestial equator and the ecliptic, produces 2 points in which they intersect, which are the equinoctial points, where the sun appears on the equinoxes. Furthermore, if we draw another great circle through the two poles, it will cut these two circles at right angles at the points at which the two circles are furthest apart from each other, known as the solstices. So this chapter serves as a bit of a primer on the motions of the various objects as well as the great circles of the celestial sphere. Chapter 9 is extremely short and is simply Ptolemy stating that his first demonstration will be to determine the size of the arc between the aforementioned poles along the great circle drawn through them. Today, we call this the obliquity of the ecliptic. Before addressing that topic, Ptolemy takes a detour to teach us some math. Much of the math that we take for granted today hadn't been developed in Ptolemy's time. Ptolemy isn't able to solve right triangles with sine and cosine. Instead, he uses a geometrical solution in which a similar unit triangle is inscribed in a unit circle, and then uses a relationship between the angles and chords to solve for the unknown portions. He can then relate this similar triangle to the one in question to determine the unknown parts. But to do any of that, he'll need to know what the relationship between the chords and central angles are in his unit circle. To do that, Ptolemy lays out a table of these angles and associated chords in half-degree increments from 0 to 180 degrees. However, Ptolemy is going to do this from first principles, so he's going to show us exactly how these relationships were determined, which is the subject of Chapter 10. I won't go through them in depth here, but since this is the first time we've encountered any math, it's worth noting that Ptolemy doesn't work in decimal. Rather, he uses a base 60 system, known as sexagesimal. This may sound scary, but you're actually more familiar with it than you think, as there's 60 seconds per minute and 60 minutes per hour. That pattern doesn't continue as there's 24 hours in a day, but if we continue that pattern in both directions, that's all sexagesimal really is. Again, I'll cover this more in a future video on the mathematical techniques of the Almagest. But for now, I'll only go so far as to state that he begins with some central angles that are easy to calculate, 36, 60, 72, 90, 108, 120, and 144 degrees. But beyond these relatively easy cases, calculating the chords of the angles begins to get trickier, and Ptolemy can't calculate them directly with the same ease. So he introduces a theorem, now referred to as Ptolemy's theorem, as the Almagest is the oldest reference to it, although it's unclear if Ptolemy actually invented it. This allows Ptolemy to derive a formula for the chord of difference. For example, since we know the chords of 72 degrees and 60 degrees, this formula allows him to work out the chord of 12 degrees, which is 72 minus 60. No, it's not simply the difference of the chords. Similarly, he derives formulas to determine the chord of half an angle he already knows the angle-chord relationship for, as well as what happens when you have the sum of angles. And with a little help from a theorem from Aristarchus, he's able to determine the length of any chord for each half-degree interval from 0 to 180 degrees. And that is laid out in Chapter 11, the entirety of which is the presentation of that table. Returning to the question of the angle between the two great circles, the obliquity of the ecliptic, Ptolemy determines this observationally and introduces two instruments which both serve the same function, to measure the angle of the sun above the horizon. The first is a ring divided into 360 degrees, with an inner ring that can rotate. The inner ring has a raised piece on either side, placed diametrically opposite from one another. When the one towards the sun casts a shadow on the rear one, it is directly aligned with the sun, and the angle can be read off the outer ring. A second instrument is even simpler, a quadrant drawn on a vertical surface with a nail at the center point from which the quadrant is taken. To use these instruments to determine the obliquity of the ecliptic, the observer would measure the angle of the sun above the horizon at local noon, i.e. when it's directly south, on the equinoxes, and then compare that to the same angle on the solstices. The difference between the two is the obliquity of the ecliptic. Ptolemy gives his value as 23 degrees 51 minutes and 20 seconds, or 23.85 degrees, which is a bit high. The value changes over time, but in Ptolemy's era, it was around 23.7 degrees. With this in hand, Ptolemy's nearly ready to start working out some things on the celestial sphere. In particular, he tells us that he intends to determine what the length of the arc between the ecliptic and celestial equator is at different points around these two circles. The value Ptolemy just derived is the extreme. It decreases on either side of this, reaching 0 when the circles intersect, and then increasing again until it reaches the same value in the opposite direction at the other pole. However, all the math you've learned in high school is designed to work on flat surfaces, and the surface of a sphere is anything but. As such, Ptolemy is going to have to teach us some basics of solving problems when they're on a sphere. With a few preliminary proofs, Ptolemy derives his one tool he uses to solve these types of problems, Menelaus' theorem, named after Menelaus of Alexandria. If you're furiously Googling this theorem, be warned, the version of this theorem that you find most frequently is actually meant for flat surfaces. The version Ptolemy gives is tailored for spheres. Ultimately, Ptolemy works out two versions of the theorem, both of which function fairly similarly as they both involve segments of four intersecting great circles on the celestial sphere, the arcs they make as they intersect, and the chords of those arcs. You may be wondering where we're going to find so many great circles, as we've really only talked about two so far, the celestial equator and the ecliptic. We find out how Ptolemy intends to address this in Chapter 14, and it involves making use of some great circles that aren't cool enough to get special names. One of them will be the great circle that's perpendicular to the celestial equator and passes through the point in question along the ecliptic. And he also makes use of a great circle drawn through the two solstices. Ptolemy then walks us through an example calculation for the arc between the celestial equator and the ecliptic 30 degrees along the ecliptic from the vernal equinox. Behind the scenes, Ptolemy then repeats this calculation for 1 degree increments along the ecliptic from 0 to 90 degrees, which is all he needs to do since it's symmetrical about the solstices. The results of these calculations are laid out in a table, which is the entirety of Chapter 15. So, what use is knowing all of this? Well, it's something we'll be using quite a bit, as this just gave us a new segment of a great circle we now know things about for future use in other applications of Menelaus' theorem. And the first application Ptolemy gives us is to find the amount of time it takes for segments of the ecliptic to cross the horizon at Sphera Recta, which is a term that, even if you like astronomy, I bet you haven't heard before. I know I sure hadn't. It literally translates as the upright sphere, and essentially refers to the view from the terrestrial equator, in which the celestial equator is perpendicular to the horizon. Returning to the topic for this chapter, because the ecliptic is at an angle with respect to the celestial equator, equal arcs of it don't rise in equal intervals of time. Ptolemy wants to know how long it takes a given 10-degree arc to rise. This he calculates in time degrees. In other words, he gives the answer in degrees instead of hours, minutes, and seconds. However, one can convert to hours, minutes, and seconds by taking the same proportion of 24 hours as the value given is of a full circle, or 360 degrees. What Ptolemy demonstrates is that the segments of the ecliptic nearest the solstices take longer to rise than the ones nearer to the equinoxes. And that's all for Book 1. As discussed in Book 1, Chapter 2, Ptolemy now needs to inquire about the effect that varying the latitude of the observer will have on their view of the night sky. Changing their longitude just changes what we refer to as the time zone, but increasing or decreasing the latitude rotates the whole sky. The more north you go, the higher the northern constellations appear in your night sky. Similarly, the more southern constellations sink below the southern horizon. To get us ready, Ptolemy starts Book 2 off with a bit of geography. He states that if the whole of the world were divided into quarters by the equator and a great circle drawn through the terrestrial poles, then we would be in the northwestern section. As evidence that we're in the northern hemisphere, he notes that the shadow of a gnomon of a sundial, the part that casts the shadow, always points north, meaning that the sun is to the south. The statement on longitude is a bit more of a cheat, since Ptolemy could have imagined this in any orientation and declared himself either to be in the east or the west. But keep in mind that, in the 2nd century, his knowledge of geography would have been of Europe, Africa, and Asia. Africa was simply south, so he was really asking which was more western between Europe and Asia. And based on the previously mentioned fact that eclipses appear to happen later in the same day, when the observer is more towards Asia than Europe, he can confidently state that he's further west. Turning back towards astronomy, Ptolemy proposes 7 points which might be considered most appropriate to study. The first will be how far the celestial poles are from the horizons at various locations, which is effectively asking the same question as the distance of the zenith, the point straight up in the sky from your location, is from the celestial equator as measured along the meridian. Second, he asks, for what regions is the sun able to pass through the zenith, as well as when and how often this occurs? Third, what is the ratio of the shadows of the sun on the equinox versus the solstice? Fourth, the difference in the lengths of the longest and shortest days. Fifth, how quickly the length of the day and night changes, day to day. Sixth, what arc of the celestial equator rises or sets with a certain arc of the ecliptic. And lastly, he says that we will explore particulars and quantities of angles between the more important great circles. However, instead of addressing any of the questions Ptolemy just told us he was interested in, he goes off in another direction, asking how to find the arc of the horizon between the celestial equator and a given point of the ecliptic for various latitudes. As is often the case, Ptolemy provides an example problem. He works it for an observer in Rhodes, Greece, which Ptolemy believed to be at 36 degrees north latitude, and takes the point of the winter solstice of the ecliptic to be just rising on the horizon. Essentially, what Ptolemy is asking is how far that point, the winter solstice, on the ecliptic is away from the celestial equator along our horizon. This is a bit of a funny way to phrase the question because the celestial equator always crosses the horizon due east and due west. So what Ptolemy's really asking is how to find how far away from due east the ecliptic crosses the horizon at various latitudes at different times. As a more general case, asking how far away from east something rises is known as the ortive amplitude. I'm not going to walk through Ptolemy's example problem, but this is one of those spherical geometry problems that makes use of Menelaus's theorem. The 4 great circles involved are the celestial equator, the horizon, the observer's meridian, and a great circle drawn in through the celestial pole and the winter solstice, which is on the horizon. It gives a Menelaus configuration looking something like this. In the next chapter, Ptolemy discusses how to use the information on the length of the longest day, the summer solstice, to be able to calculate the altitude of the North Celestial Pole above the horizon. This problem is not particularly different from the previous one and uses an almost identical application of Menelaus's theorem. Next, Ptolemy looks at how often the sun reaches the zenith at various latitudes. This isn't really a calculation so much as a visual understanding of the celestial sphere. Discussing this in modern astronomy. As the Earth rotates beneath the celestial sphere, the zenith point will trace out a small circle about the celestial sphere. As a quick statement, the small circle that the zenith traces out is going to be as far away from the celestial equator as is the latitude for the observer. So, if you're on the terrestrial equator, then your zenith will be 0 degrees from the celestial equator, essentially tracing it. If you're at 10 degrees north latitude, your zenith will trace out a small circle 10 degrees above the celestial equator. In short, your zenith will trace your line of latitude onto the celestial sphere each day. Understanding this, it means that the most northerly point at which the sun can pass through the zenith is the latitude equal to the obliquity of the ecliptic, which again Ptolemy previously gave as 23.85 degrees. At that latitude, on and only on the solstice, the sun will touch the zenith. At all lower latitudes, it will pass through the zenith on 2 days, once as it moves northward and once as it returns southward. At higher latitudes, the sun cannot cross through the zenith. But when does this happen? Ptolemy tells us that we can actually use the table of inclinations that he created in Book 1, Chapter 15, to figure this out by looking up the latitude in question. We then take the corresponding value as a fraction of 360 degrees and determine what proportion of a year that is. Add and subtract that from the date of the summer solstice to figure out the dates that the sun passes through the zenith. Ptolemy doesn't stop to explain why this works, it's simply left as a sort of a neat trick. Next, Ptolemy asks how we can derive the ratio of the length of a sundial's gnomon on the solstice versus the equinox. This is a pretty straightforward high school trig problem, only complicated by the fact that Ptolemy didn't have high school trig. So he has to apply his best method of solving right triangles to solve it. Ptolemy has laid out these last few chapters because, in chapter 6, he goes through the various terrestrial latitudes and talks about how the sky would look in each of them. He begins with the terrestrial equator and works his way northwards, defining a total of 39 zones. For each, he describes the length of the longest day, which direction the shadows of the gnomons point, and how long the days are on the equinox and solstice. At many latitudes, he also lists a major city. This chapter feels very out of place in the Almagest as a whole, and the translator, G.J. Toomer, makes it clear in the footnotes that this is something of a fossil from an earlier astronomical tradition, in which this information had some uses. But as far as the Almagest goes, we never actually use this information again. Ptolemy then returns to the question of how long various arcs of the ecliptic take to rise with various parts of the celestial equator, but now for the more complicated case in which the observer isn't on the terrestrial equator. The math gets a bit more complicated, but Ptolemy is still able to exploit some symmetries about the solstices and equinoxes to save himself some work. He first proves these symmetries and then works through another example problem for us. Having shown us how to do the math, Ptolemy again does the rest of it behind the scenes and gives us the results in a handy table which has several columns, calculated for the various latitudes. But not all 39 he went through back in chapter 6. Instead, he picks 11 that he finds especially important. This has been a lot of work, so Ptolemy spends a chapter illustrating some of the handy things we can determine from this table. The first thing that he tells us we can do is to determine the length of a day at various times throughout the year. Second, we can convert to what are known as seasonal hours, which I should pause to explain. In modern timekeeping, we divide the day into 24 hours of equal length, referred to as equal hours. However, this wasn't how it was always done. For much of the medieval period and the era prior, it was quite common to simply divide the day and night each into 12 hours. On the equinoxes, this would be the same as the equal hours. However, during the summer, when the days are longer, the daytime hours would have to be stretched and are longer than the equal hours. Conversely, at night during the summer, the seasonal hours are shorter than an equal hour. This is an annoying system, but will actually be important later on when Ptolemy needs more ancient records which were recorded in the unequal hours system. Thus, he needs to understand what it means in terms of the equal hours so that he can work with these observations. Next, Ptolemy gives the most significant nod to astrology in the entire Almagest by telling us that these rising timetables are helpful for determining what zodiac sign was on the horizon at a given time. Ptolemy doesn't explicitly call this out as astrological, but at the end of the day, this is known as the ascendant sign. Another application with potential uses in astrology is finding what point of the zodiac is on the observer's meridian at a given time. Again, Ptolemy doesn't explicitly tie this to astrology, but this is the culminating sign, as culminating means on the meridian, and is divided into an upper culmination, when something crosses the portion of the meridian above the horizon, and a lower one, when it crosses the portion of the meridian below the horizon. We're also told that we can go backwards, and if we know how high above the horizon something culminated, we can determine where along the horizon it would have risen. The next several chapters are Ptolemy showing how to work out various other angles on the celestial sphere. In chapter 10, he demonstrates how to find the angle between a point on the ecliptic and the observer's meridian. In chapter 11, he demonstrates how to find the angle the ecliptic makes with the horizon. In chapter 12, Ptolemy explores two topics. The first is the angle made between the ecliptic and an altitude circle. An altitude circle is simply another great circle that goes through the observer's zenith, which is the pole of the horizon, and some other point. The meridian, which we've discussed previously, is simply a special case of an altitude circle, where the second point is the points due north or due south. Ptolemy picks his points that the altitude circle will be going through as the various points along the ecliptic. But the manner in which he chooses the points along the ecliptic is initially rather odd. He chooses them based on how long it will be until that point reaches the observer's meridian in hourly increments. This means that the calculation will make use of the rising timetables to determine some of the arcs involved in the calculation, so we're starting to see how the Almagest builds upon itself. In addition, Ptolemy also demonstrates how to calculate the distance of these points from the observer's zenith. Before beginning chapter 13, I'll pause briefly to say that the calculations we've introduced have seemed pretty random and arbitrary. However, they will be coming into play well down the road. Specifically, we'll be coming back to this information in Book 5 and Book 6, where we deal with the moon, because the moon is close enough to exhibit parallax, and this information will be needed to determine just how much. However, there's a lot that goes into determining the lunar parallax. This includes what point on the ecliptic we're referring to, how long before that point culminates, the angle that the ecliptic is inclined with respect to the altitude circle at a given point in time, and the observer's latitude. These are all things we've just discussed. Like many of the calculations on the celestial sphere, this one gets annoyingly complicated. So Ptolemy does as he's done before and summarizes the results in a table. But because there's so many factors, this table is by far the largest we've encountered so far. He goes through the same 11 latitudes he used in the table of rising times from chapter 8 in this book. For each one, he takes the first point of each zodiac sign and calculates the angles and zenith distances when it is culminating, and for an integer hours before and after noon. This means that we have 11 latitudes, each with 12 signs, each with an average of 6 hours before or after noon, resulting in about 800 entries in this table. I'm quite glad that Ptolemy did the math for us and instead only gives us an example calculation. And that's the end of Book 2. To recap, Books 1 and 2 were mostly set up for what will come later. Ptolemy has derived from first principles the tools that he'll need to be able to solve right triangles, taught us how to do math on the celestial sphere, introduced several important great circles, and provided us with some nifty tables that will become important as we go. In the next video, I'll explore Book 3, in which Ptolemy introduces the eccentric and epicyclic models to explain the complicated motion of the wandering bodies, and then he will adopt the former to develop his model for the sun. So, join me next time as we continue exploring how Ptolemy defined astronomy before the telescope.